Describe and explain results. Width. Site 1 was the narrowest with a maximum width of 5.1. Site 2 was wider with a maximum width of 8.4. And Site 3 was the widest with a maximum width of 15.9 meters. Explanation. At Site 1, near the upper course, the river had less discharge and energy, so it mainly eroded vertically, creating a narrow, steep-sided channel. The upper course of the channel is narrow because the river has a low discharge and focuses its energy on vertical erosion. Vertical erosion is the downwards erosion that makes the riverbed deeper.
At Site 2, the river travelled downstream. Tributaries join, increasing the volume of water and therefore the river's energy. Tributaries are streams or lakes that flow into larger rivers. This allowed more lateral erosion to occur through a process such as hydraulic action. Lateral erosion is the sideways wearing away of the riverbank by a river. Hydraulic action is when the sheer force of the water forces air into cracks, causing the rocks to be dislodged. Over time, these processes widen the channel. By Site 3, the river had a much greater discharge and more energy due to the added tributaries downstream. This increased volume of water allowed the river to erode more laterally than vertically, widening the channel. Hydraulic action became more effective at wearing away the riverbanks, creating a broader and more open channel. The river's flow became smoother and slower, allowing both erosion and deposition to shape a wider channel. Deposition is when sediments or rocks are transported along the river by the water's energy. Depth. Site 1 was the shallowest with a maximum depth of 27 centimetres. Site 2 was deeper with a maximum depth of 35 centimetres, and Site 3 was the deepest with a maximum depth of 53 centimetres. Explanation. At Site 1, the river had a smaller discharge and less energy of water, so it mainly eroded vertically through abrasion, but only within a narrow and shallow channel. Abrasion is when rocks in the water are dragged along the riverbed, grinding it down. As the river flows downstream to Sites 2 and 3, tributaries join the main channel, see point C on datasheet, increasing the overall discharge and erosive power. This greater energy allows the river to erode vertically and more effectively, deepening the channel. Variations in flow speed along the riverbed also
lead to the formation of pools and riffles. Pools are deeper areas formed by stronger downward erosion where water flow is faster, while riffles are shallower sections created by deposition where flow is slower. The increase of discharge and energy downstream results in greater vertical erosion, creating a deeper channel. Rock size. Site 1 had the biggest rock size at 13.7 centimetres. Site 2 had a smaller rock size at 10.5 centimetres. And Site 3 had the smallest rock size at 7.7 centimetres. Explanation. At Site 1, rocks are larger because they had experienced limited erosion because of a low flow and less force in the water. At Site 2, as the river flowed downstream, processes such as attrition and abrasion occurred, which further reduced the rock size. Attrition is when waves cause rocks to hit off each other and break into smaller pieces. Siltation also happened, and this is a process where sediment, like pebbles and large sand grains, move along the riverbed. By Site 3, the river's energy and longer transport distance meant the load had been eroded and rounded significantly by attrition and suspension. Suspension is the transport of fine sediments such as clay or silt that are dragged along by the water, contributing to the breakdown of the rocks, resulting in much smaller rock sizes. There has also been a river beach formed, which is a slope made of deposition sediment, such as sand and shingle, created because the water slows down on the inside of the curve, losing its energy and dropping the material it was carrying. Gradient. At Site 1, there is the presence of the V-shaped valley, which is steep. It is high up, so the land hasn't been eroded. A V-shaped valley is formed in the upper course of the river by vertical erosion and crumbles on the valley sides, which breaks down the rock. There are also steep contour lines, see point F on datasheet. So this means there is not much erosion at all in this area. There is a waterfall between Site 1 and Site 2. The formation of a waterfall includes the process of a steep-sided gorge. A steep-sided gorge forms in the upper course of a river where a layer of hard rock lies over a softer rock, which can explain why Site 1 and Site 2 are steeper. At Site 2, more lateral erosion is happening here. The river is gaining more power. Contour lines are less steep. At Site 3, a meander has formed, which is a middle to lower course feature. A meander is a looping bend in a river. Lateral erosion is more apparent than vertical erosion, which means the river is widening more than it is deepening. The inside bend of the meander is causing more deposition of the river's load. This is causing the river to flatten the land as it is building up a gentle slope rather than eroding it away. This area is more urbanized as a suburban area, so it has been flattened over time with human activity. See point H on map. Velocity. At Site 1, the river is slow because of low flow and large rocks are not allowing the river to flow smoothly. Riffles are shallow and turbulent due to these rocks in the river creating friction, slowing the river down. At Site 2, the river is faster because there is a tributary confluence. A confluence is the point where a tributary joins onto the main river. This increases the discharge, the volume of water flowing in the channel, which gives the river more energy. With greater energy, the river experiences less friction relative to its total volume, allowing water to flow more effectively and at a higher velocity. Steep contour lines which are found in this area mean there was a fast surface runoff, which explains why the river at Site 2 is faster. Surface runoff is water from precipitation that runs along the land surface when the ground cannot absorb any more water. The area where the field work was conducted experienced heavy rain recently, and so this created a greater surface runoff in the area. At Site 3, the river was the fastest due to the pools found on the outside bend of the meander. These pools are deeper areas of the river which allow a faster flow as there is less friction from the riverbed, slowing down the water, allowing an uninterrupted flow to gain speed. Riffles and pools lead to changes in speed and depth in the river channel. The power of the river is making rocks tiny because of attrition and solution, and so the river isn't weighed down by large rocks, making the speed of the river faster. Conclusion. For my first hypothesis, I predicted that the river's width and depth would increase the further I traveled downstream. I can now confidently say that the river's width and depth did increase downstream as I predicted, as it widened by 10.8 meters and got deeper by 26 centimeters. Therefore, it has similar characteristics to the Bradshaw model. Reasons for this could be due to Site 1's proximity to the source and therefore having low flow. As the river travels downstream, it gains water from tributaries and increases its erosional power, causing it to get deeper. For my second hypothesis, I predicted that the velocity of the river would increase as I get further from the source. I can now confidently say that the river's velocity did increase as I got further from the source, as it sped up by. Therefore, it has similar characteristics to the Bradshaw model. Reasons for this could be due to the low flow, large rocks, and unsettled riffles at Site 1, causing the river to travel unevenly and slowly. At Site 2, a tributary joined the main river, which caused the river velocity to speed up, as it gave the river more energy and power. As I travelled further, the rocks in the river were smaller, as the river's erosive power was breaking the large rocks apart, which also sped up the velocity of the water and made the flow smoother. Overall, the Bradshaw model was useful because it mostly fit the sites of the rivers I investigated, and it was helpful to compare.